calculations. But again, if you look at something like VO, our video generation model, it can model liquids quite well, surprisingly well, and materials, specular lighting. I love the ones where, there's people who generate videos where there's like clear liquids going through hydraulic presses and then it's being squeezed out. I used to write physics engines and graphics engines in my early days in gaming, and I know it's just so painstakingly hard to build programs that can do that, and yet somehow these systems are reverse engineering from just watching YouTube videos. So presumably what's happening is it's extracting some underlying structure around how these materials behave. So perhaps there is some kind of lower dimensional manifold that can be learned if we actually fully understood what's going on under the hood. That's maybe true of most of reality.
The following is a conversation with Demis Hassabis, his second time on the podcast. He is the leader of Google DeepMind and is now a Nobel Prize winner. Demis is one of the most brilliant and fascinating minds in the world today, working on understanding and building intelligence and exploring the big mysteries of our universe. This was truly an honor and a pleasure for me. This is the Lex Fridman podcast. To support it, please check out our sponsors in the description and consider subscribing to this channel. And now, dear friends, here's Demis Hassabis. In your Nobel Prize lecture, you propose what I think is a super interesting conjecture that, quote, any pattern that can be generated or found in nature can be efficiently discovered and modeled by a classical learning algorithm. What kind of patterns or systems might be included in that? Biology, chemistry, physics, maybe cosmology, neuroscience? What are we talking about?
Sure. Well, look, I felt that it's sort of a tradition, I think, of Nobel Prize lectures that you're supposed to be a little bit provocative, and I wanted to follow that tradition. What I was talking about there is if you take a step back and you look at all the work that we've done, especially with the AlphaX projects, so I'm thinking AlphaGo, of course, AlphaFold, what they really are is we're building models of very combinatorially high dimensional spaces that, if you try to brute force a solution, find the best move and go, or find the exact shape of a protein, and if you enumerated all the possibilities, there wouldn't be enough time in the time of the universe. So you have to do something much smarter. And what we did in both cases was build models of those environments, and that guided the search in a smart way, and that makes it tractable. So if you think about protein folding, which is obviously a natural system, why should that be possible? How does physics do that? Proteins fold in milliseconds in our bodies. So somehow physics solves this problem that we've now also solved computationally. And I think the reason that's possible is that in nature, natural systems have structure because they were subject to evolutionary processes that shaped them. And if that's true, then you can maybe learn what that structure is.
So this perspective, I think, is a really interesting one. You've hinted at it, which is almost like crudely stated. Anything that can be evolved can be efficiently modeled. Think there's some truth to that?
Yeah, I sometimes call it survival of the stablest or something like that, because it's of course there's evolution for life, living things, but there's also if you think about geological time, so the shape of mountains, that's been shaped by weathering processes, right, over thousands of years. But then you can even take it cosmological, the orbits of planets, the shapes of asteroids. These have all been survived kind of processes that have acted on them many, many times. So if that's true, then there should be some sort of pattern that you can kind of reverse learn, and a kind of manifold really that helps you search to the right solution, to the right shape, and actually allow you to predict things about it in an efficient way, because it's not a random pattern, right? So it may not be possible for man-made things or abstract things like factorizing large numbers, because unless there's patterns in the number space, which there might be, but if there's not and it's uniform, then there's no pattern to learn. There's no model to learn that will help you search. You have to do brute force. So in that case, you maybe need a quantum computer, something like this. But in most things in nature that we're interested in are not like that. They have structure that evolved for a reason and survived over time. And if that's true, I think that's potentially learnable by a neural network.
It's like nature's doing a search process, and it's so fascinating fascinating that it's in that search process is creating systems that can be efficiently modeled.
That's right. Yeah.
So interesting.
So they can be efficiently rediscovered or recovered, because nature's not random, right? Everything that we see around us, including like the elements that are more stable, all of those things, they're subject to some kind of selection process, pressure.
Do you think, because you're also a fan of theoretical computer science and complexity, do you think we can come up with a kind of complexity class, like a complexity zoo type of class, where maybe it's the set of learnable systems, the set of learnable natural systems, LNS?
Yeah.
This is a Demis Hassabis new class of systems that could be actually learnable by classical systems in this kind of way, natural systems that can be modeled efficiently.
Yeah. I mean, I've always been fascinated by the P equals NP question and what is modelable by classical systems, i.e. non-quantum systems, Turing machines in effect. And that's exactly what I'm working on actually in kind of my few moments of spare time with a few colleagues about should there be, maybe a new class of problem that is solvable by this type of neural network process and kind of mapped onto these natural systems. So, the things that exist in physics and have structure. So I think that could be a very interesting new way of thinking about it. And it sort of fits with the way I think about physics in general, which is that, I think information is primary. Information is the most sort of fundamental unit of the universe, more fundamental than energy and matter. I think they can all be converted into each other, but I think of the universe as a kind of informational system.
So when you think of the universe as an informational system, then the P equals NP question is a physics question.
That's right.
And it's a question that can help us actually solve the entirety of this whole thing going on.
Yeah, I think it's one of the most fundamental questions, actually, if you think of physics as informational. And the answer to that, I think, is going to be, very enlightening.
More specific to the P and NP question, this, again, some of the stuff we're saying is kind of crazy right now. Just like the Christian Atkinson Nobel Prize speech, controversial thing that he said sounded crazy, and then you went and got a Nobel Prize for this with John Jumper, solved the problem. So let me just stick to the P equals NP. Do you think there's something in this thing we're talking about that could be shown if you can do something like polynomial time or constant time compute ahead of time and construct this gigantic model, then you can solve some of these extremely difficult problems in a theoretical computer science kind of way?
Yeah, I think that there are actually a huge class of problems that could be couched in this way, the way we did AlphaGo and the way we did AlphaFold, where you model what the dynamics of the system is, the properties of that system, the environment that you're trying to understand, and then that makes the search for the solution or the prediction of the next step efficient. Basically polynomial time, so tractable by a classical system, which a neural network is. It runs on normal computers, right? Classical computers, Turing machines in effect. And I think it's one of the most interesting questions there is how far can that paradigm go? I think we've proven, and the AI community in general, that classical systems, Turing machines, can go a lot further than we previously thought. They can do things like model the structures of proteins and play Go to better than world champion level. And, a lot of people would have thought maybe 10, 20 years ago that was decades away, or maybe you would need some sort of quantum machines to quantum systems to be able to do things like protein folding. And so I think we haven't really even sort of scratched the surface yet of what classical systems, so-called, could do. And of course, AGI being built on a neural network system on top of a neural network system on top of a classical computer would be the ultimate expression of that. And I think the limit, what the bounds of that kind of system, what it can do, it's a very interesting question and directly speaks to the P equals NP question.
What do you think, again, hypothetical, might be outside of this? Maybe emergent phenomena? Like if you look at cellular automata, you have extremely simple systems and then some complexity emerges.
Yes.
Maybe that would be outside, or even, would you guess even that might be amenable to efficient modeling by a classical machine?
Yeah, I think those systems would be right on the boundary, right? So I think most emergent systems, cellular automata, things like that, could be modelable by a classical system. You just sort of do a forward simulation of it and it'd probably be efficient enough. Of course, there's the question of things like chaotic systems where the initial conditions really matter, and then you get to some, uncorrelated end state. Now, those could be difficult to model. So I think these are kind of the open questions. But I think when you step back and look at what we've done with the systems and the problems that we've solved, and then you look at things like VO3 on like video generation, sort of rendering physics and lighting and things like that, really core fundamental things in physics. It's pretty interesting. I think it's telling us something quite fundamental about how the universe is structured, in my opinion. So, in a way, that's what I want to build AGI for, is to help us as scientists answer these questions like P equals MP.
Yeah, I think we might be continuously surprised about what is modelable by classical computers. I mean, AlphaFold 3 on the interaction side is surprising that you can make any kind of progress on that direction. Alpha Genome is surprising that you can map the genetic code to the function. Kind of playing with the emergent kind of phenomena, you think there's so many combinatorial options and then here you go. You can find the kernel that is efficiently modeled.
Yes, because there's some structure, there's some landscape, in the energy landscape or whatever it is that you can follow, some gradient you can follow. And of course, what neural networks are very good at is following gradients. And so if there's one to follow and you can specify the objective function correctly, you don't have to deal with all that complexity, which I think is how we maybe have naively thought about it for decades, those problems. If you just enumerate all the possibilities, it looks totally intractable. And there's many, many problems like that. And then you think, well, it's like 10 to the 300 possible protein structures, 10 to the 170 possible go positions. All of these are way more than atoms in the universe. So how could one possibly find the right solution or predict the next step? But it turns out that it is possible. And of course, reality, nature does do it, right? Proteins do fold. So that gives you confidence that there must be, if we understood how physics was doing that, in a sense, and we could mimic that process, i.e. model that process, it should be possible on our classical systems, is basically what the conjecture is about.
And of course, there's nonlinear dynamical systems, highly nonlinear dynamical systems, everything involving fluid.
Yes, right.
I recently had a conversation with Terence Tao, who mathematically it contends with a very difficult aspect of systems that have some singularities in them that break the mathematics. And it's just hard for us humans to make any kind of clean predictions about highly nonlinear dynamical systems. But again, to your point, we might be very surprised what classical learning systems might be able to do about even fluid.
Yes, exactly. I mean, fluid dynamics, Navier-Stokes equations, these are traditionally thought of as very, very difficult, intractable kind of problems to do on classical systems. They take enormous amounts of compute, weather prediction systems, these kind of things all involve fluid dynamics calculations. And, but again, if you look at something like our video generation model, it can model liquids quite well, surprisingly well. And materials, specular lighting. I love the ones where, there's people who generate videos where there's like clear liquids going through hydraulic presses and then it's being squeezed out. I used to write physics engines and graphics engines in my early days in gaming, and I know it's just so painstakingly hard to build programs that can do that. And yet somehow these systems are, reverse engineering from just watching YouTube videos. So presumably what's happening is it's extracting some underlying structure around how these materials behave. So perhaps there is some kind of lower dimensional manifold that can be learned if we actually fully understood what's going on under the hood. That's maybe true of most of reality.
Yeah, I've been continuously, precisely by this aspect of VO3. I think a lot of people highlight different aspects, including the comedic and the meme,
yes,
all that kind of stuff. And then the ultra realistic ability to capture humans in a really nice way that's compelling and feels close to reality, and then combine that with native audio. All of those are marvelous things about VO3, but exactly the thing you're mentioning, which is the physics.
Yeah.
It's not perfect, but it's pretty damn good. And then the really interesting scientific question is, what is it understanding about our world in order to be able to do that? Because of the cynical take with diffusion models, there's no way it understands anything. But it seems, I don't think you can generate that kind of video without understanding. And then our own philosophical notion of what it means to understand then is like brought to the surface. Like, To what degree do you think VO3 understands our world?
I think to the extent that it can predict the next frames, in a coherent way, that is a form, of understanding, right? Not in the anthropomorphic version of, it's not some kind of deep philosophical understanding of what's going on. I don't think these systems have that, but they certainly have modeled enough of the dynamics, put it that way, that they can pretty accurately generate whatever it is, 8 seconds of consistent video that by eye, at least, at a glance, is quite hard to distinguish what the issues are. And imagine that in 2 or 3 more years' time. That's the thing I'm thinking about, and how incredible they will look, given where we come from, the early versions of that 1 or 2 years ago. And so the rate of progress is incredible. And I think, unlike you, it's like a lot of people love all of the stand-up comedians, and that actually captures a lot of human dynamics very well, and body language. But actually, the thing I'm most impressed with and fascinated by is the physics behavior, the lighting and materials and liquids, and it's pretty amazing that it can do that. And I think that shows that it has some notion of at least intuitive physics, right? How things are supposed to work intuitively, maybe the way that a human child would understand physics, right? As opposed to a PhD student really being able to unpack all the equations. It's more of an intuitive physics understanding.
Well, that intuitive physics understanding, that's the base layer. That's the thing people sometimes call like common sense.
Mm-hmm.
Like it really understands something. I think that really surprised a lot of people. It blows my mind that I just didn't think it would be possible to generate that level of realism without understanding.
Mm.
There's this notion that you can only understand the physical world by having an embodied AI system, a robot that interacts with that world. That's the only way to construct an understanding of that world.
Yeah.
But VO3 is directly challenging that.
Right.
It feels like.
Yes, and it's very interesting. Even if you were to ask me 5, 10 years ago, I would have said, even though I was immersed in all of this, I would have said, well, yeah, you probably need to understand intuitive physics. Like if I push this off the table, this glass, it will maybe shatter. And the liquid will spill out, right? So we know all of these things. But I thought that, and there's a lot of theories in neuroscience, it's called action in perception, where, you need to act in the world to really, truly perceive it in a deep way. And there was a lot of theories about you need embodied intelligence or robotics or something, or maybe at least simulated action, so that you would understand things like intuitive physics. But it seems like you can understand it through passive observation, which is pretty surprising to me. And again, I think hints at something underlying about the nature of reality, in my opinion, beyond just the cool videos that it generates. And of course, there's next stages is maybe even making those videos interactive, so one can actually step into them and move around them, which would be really mind-blowing, especially given my games background. So you can imagine. And then I think we're starting to get towards what I would call a world model, a model of how the world works, the mechanics of the world, the physics of the world, and the things in that world. And of course, that's what you would need for a true AGI system.
I have to talk to you about video games. So
yes.
You were being a bit trolly. I think you're having more and more fun on Twitter, on X, which is great to see. So a guy named Jimmy Apples tweeted, "Let me play a video game of my VO3 videos already. Google cooked so good. Playable world models when," spelled WEN question mark. And then you quote tweeted that with, "Now wouldn't that be something?" So how hard is it to build game worlds with AI? Maybe can you look out into the future of video games 5-10 years out? What do you think that looks like?
Well, games were my first love, really, and doing AI for games was the first thing I did professionally in my teenage years, and was the first major AI systems that I built. And I always want to scratch that itch one day and come back to that. So, and I will do, I think. And I think I sort of dream about, what would I have done back in the 90s if I'd had access to the kind of AI systems we have today? And I think you could build absolutely mind-blowing games. And I think the next stage is, I always used to love making, all the games I've made are open world games. So they're games where there's a simulation, and then there's AI characters, and then the player interacts with that simulation, and the simulation adapts to the way the player plays. And I always thought they were the coolest games, because so games like Theme Park that I worked on, where everybody's game experience would be unique to them, right? Because you're kind of co-creating the game. right? We set up the parameters, we set up initial conditions, and then you as the player immersed in it, and then you are co-creating it with the simulation. But of course, it's very hard to program open world games. You've got to be able to create content whichever direction the player goes in, and you want it to be compelling no matter what the player chooses. And so it was always quite difficult to build things like Cellular Automata, actually, type of those kind of classical systems which created some emergent behavior. But they're always a little bit fragile, a little bit limited. Now we're maybe on the cusp in the next few years, 5, 10 years, of having AI systems that can truly create around your imagination, can sort of dynamically change the story and storytell the narrative around and make it dramatic no matter what you end up choosing. So it's like the ultimate choose your own adventure sort of game. And I think maybe we're within reach if you think of a kind of interactive version of VO, and then wind that forward 5 to 10 years and imagine how good it's going to be.
Yeah, so you said a lot of super interesting stuff there. So one, the open world, built into that is a deep personalization, the way you've described it. So it's not just that it's open world, but you can open any door and there'll be something there. It's that the choice of which door you open in an unconstrained way defines the worlds you see. So some games try to do that. They give you choice.
Yes.
But it's really just an illusion of choice
Yes.
because you're only like Stanley Parable. This game I recently played. It's really, there's a couple of doors and it really just takes you down the narrative. Stanley Parable is a great video game. I recommend people play. That kind of in a meta way mocks the illusion of choice, and there's philosophical notions of free will and so on. But I do like one of my favorite games of Elder Scrolls is Daggerfall, I believe, that they really played with it, like random generation of the dungeons.
Yeah.
Of if you could step in and they give you this feeling of an open world. And there, you mentioned interactivity. You don't need to interact. That's a first step because you don't need to interact that much. You just, when you open the door, whatever you see is randomly generated for you. And that's already an incredible experience because you might be the only person to ever see that.
Yeah, exactly. And so, but what you'd like is a little bit better than sort of a random generation, right? So you'd like, and also better than a simple A/B hard-coded choice, right? That's not really open world, right? Like, as you say, it's just giving you the illusion of choice. What you want to be able to do is potentially anything in that game environment. And I think the only way you can do that is to have generated systems that will generate that on the fly. Of course, you can't create infinite amounts of game assets, right? It's expensive enough already how AAA games are made today. And that was obvious to us back in the 90s when I was working on all these games. I think maybe Black and White was the game that I worked on, early stages of that had still probably the best learning AI in it. It was an early reinforcement learning system that you were looking after this mythical creature and growing it and nurturing it, and depending how you treated it, it would treat the villagers in that world in the same way. So if you were mean to it, it would be mean. If you were good, it would be protective. And so it was really a reflection of the way you played it. So actually all of the, I've been working on sort of simulations and AI through the medium of games at the beginning of my career, and really the whole of what I do today is still a follow-on from those early, more hard-coded ways of doing the AI to now, fully general learning systems that are trying to achieve the same thing.
Yeah, it's been interesting, hilarious, and fun to watch you and Elon obviously itching to create games because you're both gamers. And one of the sad aspects of your incredible success in so many domains of science, like serious adult stuff, that you might not have time to really create a game. You might end up creating the tooling that others will create the game. You have to watch others create the thing you've always dreamed of. Do you think it's possible you can somehow, in your extremely busy schedule, actually find time to create something like Black and White, an actual video game where, like, you could make the childhood dream become big reality?
There's two things when I think about that. Is maybe that with vibe coding, as it gets better, there's possibility that I could, one could do that actually in your spare time. So I'm quite excited about that as that would be my project if I got the time to do some vibe coding. I'm actually itching to do that. And then the other thing is, maybe it's a sabbatical after AGI has been safely stewarded into the world and delivered into the world. that, and then working on my physics theory, as we talked about at the beginning. Those would be the two my two post AGI projects. Let's call it that way.
I'll love to see which
The ultimate game.
post AGI which you choose. Solving the problem that some of the smartest people in human history contended with, P equals NP,